of China. So today our topic is about waves in the high latitudes. I'm delighted to introduce our two speakers. The first speaker is Dr. Joy Voermans from University of Melbourne. Joy does research in many aspects of ocean surface waves, particularly for the lab and the field experiments. And today he is going to introduce his recent research about the wave-ice interaction based on the satellite observations. And our second speaker is Dr. Alberto Meucci from University of Melbourne. And Alberto does research in wave climate and wave modeling. And today he's going to talk about the actual tropical cyclone-induced wave field and the modeling thing. So before we start, I also want to draw your attention, and we are searching the speakers for the December Zoominars and the Zoominar in the next year. So if you are interested to present your research, please contact us. Thank you. Okay, Joy. So I think it's yours. You can start now. Thank you.
Thank you, Xinxiang and Tom, for organizing this. Can you see my screen?
Yes, we can.
Perfect. All right, so I'll be talking on wave attenuation in sea ice derived from ICET2 measurements. I forgot to put sea ice in the title, so I hope I'm not disappointing any people with that. But that's what my talk will be about. I've never had the privilege to go on the ship and see the waves in sea ice, but luckily there are some videos online. For you to share. So normally what you see here on the left, that's closer to the ice edge. These are waves, particularly swell in this case, that are propagating through pancake ice. Sea ice is well known for attenuating the very short waves very quickly, but swell is usually left and propagates further and further until it reaches the consolidated ice on the right. And they speed up the video here 10 times so you can actually see the waves coming in. So the camera is standing fixed, so that's why the camera is in itself not moving, but you can still see the waves propagating through the ice. And it's important because during that flexure of the ice, the waves can actually break the ice in multiple pieces, and that's quite important for the thermodynamics in the sea ice models. And these waves can propagate quite far. So this was a study by Takiko Nose from the University of Tokyo. But what they did is they deployed some buoys. So you see that here, that brownish line at the bottom, which survived for almost a year. So that's quite an achievement. But at some point it was 1,250 kilometers from the ice edge, but it was still recording waves up to like 10 centimeter in significant wave height. So that's a very fast stretch, and depending on the exact wave conditions and the ice conditions, it can actually still break the ice there. So waves have quite a bit of an impact, and that's why we need to model that as accurate as possible. There are some problems though. So Haley Shen reviewed quite a bit the state of the art of the wave ice interaction modeling, and I think a fair conclusion is to say that we still don't really know that much about wave ice interactions. We have a lot of theory available, but we still haven't really decided what mechanisms are of importance, and which are not, and in what cases, etc. So the idea is that we need more observations and still more theory and understanding of the physics. And getting more observations is easiest through well, at least a large data set is easiest through satellite remote sensing. So quite a few have been doing that already, measuring waves, but not necessarily attenuation in sea ice. Some did, but it hasn't really caught up too much yet. So that's what I'll be showing here. That's the wave attenuation estimated from the ISO2 observations. And I'll do that in the marginal ice zone. So a quick definition of the marginal ice zone. So there's a qualitative description which is on the top left. But in general, that means that It's the region of sea ice that's impacted by the waves, but it's quite qualitative and you cannot really put any numbers to that. So in Brouwer et al., they use a certain definition that we'll be using here as well. So what you see on the top right is the one of the ice-set transects. So you see on the left the waves coming in. So 0 is the ice edge, and we see there's a decay of wave energy. At some point, it starts to approach 0, and then very gently we see an increase again in these fluctuations or in the variance that's measured by the ice-set laser altimeter. And the practical definition that's being used then is the marginal ice zone is defined as the transition from a wave-dominated to a sea ice-dominated regime. So what we can do is take a moving window over this transect and calculate the significant wave height or the variance or the standard deviation or something equivalent. And what we see here are two very clear trends and a clear transition as well. So again, that's the wave-dominated towards the sea-dominated or sea ice-dominated regime. And that transition, that's what we define as the marginal ice zone width. So the data that we're using is coming from Brouwer et al. So in that study, they did some quality control, and it's quite a lot of work. So that's why we're using their data. And the reason for that is that the laser altimeter is being blocked from measuring waves due to the clouds. So it's really a lot of work to get the cloud pollution out of there or the missing parts. So what we're left over with is 320 transects, which cover 4 months. The idea is that these months, they sort of represents the 4 different seasons. And the resolution is about 8 meters. So the signal is interpolated on an 8-meter horizontal resolution, and we're calculating the spectral density on windows of about 8 kilometers. And again, that's on a moving window, so that moves along the transect. And then if we have the spectral density, we can then estimate the actual attenuation rate. So we are using that for that. We take 2 spectra 16 kilometers apart, and then we are assuming an exponential decay of the wave energy. So we have the 2 spectra that are 16 kilometers apart, which is delta x. And what we're interested in is this alpha parameter, which we call the wave attenuation rate. And we do some other quality control measures, but I'm not going too much into detail of that. But we're left over with 304 transects, but most of them are actually in May and September. So what you see on the right is a map of the distribution of these of the data. So these are all these marginal ice zones that are identified in the transects, but we really see that in May, September is dominating our data set. So now the interesting part, so these are some examples of a transect. On the left, we see the sentinel image, and in the dots in black, they identify the marginal ice zone that goes from the top dot is the start, so that's the ice edge, and the end of the marginal ice zone is defined by this by that last dot. And on the right, we see the wave energy that we identify in different frequency bins in the spectra for 9, 12, 15, and 18 seconds. So what we see is very typical for waves in sea ice. So we see, for instance, the 9-second one decays quite rapidly compared to the longer waves. So the 18-second one, which is quite gentle. And if we look a little bit closer at the attenuation rate itself, we see that it's very well sorted. So the shorter waves, they attenuate much faster, so they have a higher attenuation rates than the much longer waves. So this is more or less an ideal picture of what we already know and what the data is telling us. But not all the transects look that pretty. So this is another example where that's not the case. So what we see in the top right is that in this case, this wave field or the spectrum is dominated as a peak frequency around 12 seconds. So that's really that's quite a lot of energy compared to the other frequencies. But if you go to the bottom plot, what we see is that the attenuation rate is quite messy, right? So there's not much sorting going on with wave frequency. We also see that regularly it drops below 0, which means that we have a negative attenuation rate, which means that we have wave growth. It's not impossible physically, somewhat unlikely though that it happens. What or at least has not been confirmed really with other data sets. And then suddenly halfway the marginal ice zone, we see a rapid increase of the attenuation rate, so a very steep increase of that. We do see some sorting again with wave frequency. So again, that's well aligned with what we already know of wave-ice interactions, or at least the attenuation of waves in sea ice. But the funny thing is that we would expect a change in sea ice conditions when we really see such a clear increase in the attenuation rate. But if we look at the Sentinel image, we don't really see any of that. So it doesn't really exclude any changes in sea ice because it's just a top view of the ice, I would say. But we would expect quite different sea ice conditions exactly at this particular point if that changes so drastic. So we have been looking a little bit further into that to make sure that the data is well, at least accurate and not nonsense. So we're looking first at why these fluctuations below zero occur, or why they may occur, or whether or not we can explain that. So I'll explain that by a more extreme example. So that's this particular profile. So we see that the ice edge, again, in the Sentinel image is quite complicated, right? So a very inhomogeneous sea ice. And if we see the ice set two observations, so there's the wave energy, we really see this steep decrease followed by a very steep increase in wave energy. And that continues a little bit, and later on we still see quite some increase in wave energy. So what we think is going on is that it's a methodological artifact. So there is probably a misalignment between the measurement transects, which is here identified by the dots, and the incoming wave field. And normally that may not necessarily cause this sort of fluctuations, but if we then also have a inhomogeneous sea ice cover, that can actually happen. So we're trying to illustrate that by a very simple example. So what we do is we use the Sentinel backscatter as a proxy for the attenuation rate. So I stress here that it's not accurate at all. It's just a estimate just to illustrate this principle. So the idea is that for these white pixels, we have sea ice, and therefore the attenuation rate is higher. And in black, what we normally have is open water, and then the attenuation rate will be lower. And the reason why it doesn't work, you can already see at the top of this image, is that this is probably open water, and we already see that there's a gradient in the backscatter and the intensity of the pixel. So it's definitely not a good estimator, but again, it's just purely to illustrate our point. So what we can do then is, if we establish per pixel the attenuation rate, as followed by that color bar over there, and we assume now that the waves are well aligned with the transect itself, then we see here on the right that the wave energy is monotonically decreasing, and that's purely because we are only imposing attenuation and not any source of wave energy at all. But the interesting things start to happen if we are starting to change that. So we're creating a misalignment or a difference in the direction of the measurements and the actual waves. So in this case, if we do that for 325 degrees, so they're coming a little bit from the northwest, then we see here this dark red line over there. And we see exactly that we get that very steep increase again in wave energy as well, even though we're not imposing any sources of wave energy. So that basically means is that the sea ice conditions and that misalignment is causing these fluctuations. And this, of course, will lead to a negative attenuation rate. So what's going on here is that if the waves are coming from this 325 degrees, and in this particular stretch, there's more ice present, and the wave experience more ice than a little bit next to it in this particular part. And a little bit further, exactly where the arrow is, we again have quite a lot of ice. So the waves that are originating from the Southern Ocean and they're arriving at those particular dots over here, they're experiencing completely different ice conditions. And that's what's causing these fluctuations in the observed energy along the particular transect. So if this is really true, and we think it is, this is a methodological artifact, and it's not really a physical process of wave growth. And I hope you still remember the previous one where we saw the sudden increase around halfway the marginal ice zone, and we think the same is going on there. So if you zoom out a little bit in the Sentinel image, then this is what you see, and that is here some sort of not sure if you can call it an ice hung, but there's a big blob of ice over there that stretches a little bit further from the ice edge compared to where the transect identifies the ice edge. And if you would imagine that the waves are coming from roughly 345 degrees, so again, it's a little bit from the northwest, then we see any waves arriving above halfway the marginal ice zone, so that's the top half, they experience largely open water conditions and the rest of the half sea ice conditions. But anything that arrives at the transects beyond halfway the marginal ice zone, they experience a lot of extra ice. And that causes that very rapid decay of wave energy at that particular point. And it is quite plausible because if you see here the reanalysis and hindcast data, there seems to be some sort of an agreement there that it's not coming necessarily from the north. So what we did instead is we basically assumed that we cannot really look at the individual transects and say, okay, this is what's going on. It's a little bit more complicated and requires quite some interpretation. So what we basically assume now is that some of the profiles or some of the points, we overestimate the attenuation rate, and in other points, we're underestimating it. So by averaging all the profiles, we sort of assume now that there's some sort of a overall description of attenuation in the marginal ice zone. So that's what's shown over here for a 12-second period wave, and that seems to do quite well, I must say. So we see the black line over here is the mean, and we see that the light gray edges, the outer edges, are the 25 and the 75 percentiles. So 50% of the data falls within those lines. So we see that it's pretty well sorted if we are normalizing the distance from the ice edge by means of the marginal ice zone width. And what we see is that the attenuation rate, or the mean attenuation rate in the marginal ice zone, scales linearly with distance into the marginal ice zone. We would expect very strong correlation with ice concentration and ice thickness as well. We see that even though there is some correlation, it's considerably less, and also quite some scatter. Could be different reasons, could also be that just the data that we got it from is of too low resolution. But what we think is why it's matching quite well with, or scaling quite well with the marginal ice zone width, is that any of these ice properties, including ice concentration, ice thickness, flow size, they scale all quite well with the marginal ice zone width. So the further you get from the ice edge into the ice, the higher those parameters get. So the marginal ice zone width in some way is strongly correlated with the ice properties. And we can do that for the other periods as well. So that's shown over here. So to see here on the left are the different wave periods, and we all see that for all these profiles, we see more or less a linear increase again with the distance into the marginal ice zone. We also see some sorting going on again, although we are to enter at the beginning a little bit in the confidence interval. So it's not as clear in the beginning, but at the end, it's a bit clearer. So how do these values compare with the existing literature? So this is on the top right, more or less a summary that we did before. So that was a study of wave attenuation in land fast ice, so completely consolidated ice. And we see that these values correspond quite well. So the lower bounds correspond to the extrapolated values of these linear profiles on a logarithmic scale to 0. And we can also extrapolate them to 1. That's more or less what you see here. So it fits quite well with the observations. We also know that there's a frequency dependence. So this is one of the relations that is quite popular. So that's from Mike Milan et al. We do see that the magnitude and also the trends are quite well for the higher frequencies. For the much lower frequencies, it doesn't. But there are some recent observations from large data sets that seem to show a similar sort of flattening towards the very long waves. So that seems to match quite well. There is some seasonal variability. We cannot be too confident about that. So we see here those red lines, or the warmer colors, they represent the February and December months, but we also know that we have very limited data there. So the confidence intervals are quite large. Confidence intervals are not shown, by the way. But the idea that they're higher than the mean is more related to the idea that the wave climatology in those months is a little bit milder, and also the ice edges are considerably retreated compared to the winter months. And we think that the combined effect of that means that the ice is more consolidated, so less broken up by the waves in those particular months, which will lead to higher attenuation rates. But again, these are just hypotheses. We just don't have enough data to really say much more about that. Which brings me to the conclusion. So I'm not going to summarize the previous slides. Instead, some sort of a thoughts we have about how actually we're going to use this. So we know that normally this is how we model or derive the attenuation rates in sea ice based on this alpha parameter, which makes it very difficult to get good parameterizations of this alpha because it depends on a lot of properties, including the ice properties, which are usually unknown. But what we find in this study is that the alpha, so the attenuation rate, scales more or less linearly with distance into the marginal ice zone. So we're introducing a different parameter here, beta, and that creates a slightly different formulation here, which introduces the marginal ice zone width. But now in this case, beta becomes just a function of the wave frequency, which is a little bit more fixed and predefined, as we saw in the previous slides. Obviously, we need more data for that, but it seems to work quite well. There's a bit of a problem, of course, because the marginal ice zone width, we define that based on the wave penetration into the ice. So there's a little bit of an overlap there with other parameters, but in essence, what we think is that the marginal ice zone width is pretty much defined now by the ice properties, as we saw. So ice concentration, ice thickness, flow size distribution, etc. There are some current studies ongoing in which they try to estimate the marginal ice zone with different satellites products. And we guess that if that one is known, and that seems to match quite well with the definition that we have here, it may be a little bit more easy to model the wave attenuation in sea ice, not on the short time scales, because obviously there's quite some scatter and fluctuations there, but on the larger time scales and across Antarctica, this may be a different pathway to measure to estimate waves in sea ice. So yeah, that's the end of my talk. I'm happy to answer any questions if there are any.
Okay, thank you, Joy. Any questions from the audience? We have plenty of time for the question. Tom?
I can ask one. Is there a role of directional spreading in these estimates, and can it be used to improve estimates? Directional spreading of the wave field?
Yeah, so that's quite a different topic. But at this moment, we don't really have too much information to say anything about that. So one of the problems we're facing with measuring waves in ice is that we don't have any directional statistics of that, which usually has to do with the magnetometer in the instruments. They're very hard to calibrate in that sort of regions. Ideally, we would like to have some information of that because there are some theories, such as scattering theory, that could be well tested if we would have that data. Unfortunately, we don't really have that.
And could the incoming wave field as such, before it's underneath the ice, could the directional spreading in that play a role? Its variability causing different decay rates? I'm not at all an expert in this matter, so.
Yeah, no, it could definitely be. There are quite a variety of sources where the scatter and errors are coming from. I haven't thought about it too much, to be honest. But yes, it could be. Yeah.
Thank you.
Any other question? No? Okay, Joy, I have a question. For the attenuation rate you showed as a function of MIZ widths, I see it's peaked around the normalized width around 0.9. Yes, for example, this figure.
Yes.
So the attenuation peaked around 0.9, right? So do you have any specific explanation for this?
Yes. So what I think is happening is we're getting very close to the edge, right, of the marginal ice zone, and the marginal ice zone was identified as means of the where the wave-dominated regime goes into a sea ice-dominated regime. So the noise introduced by sea ice gets larger and larger the closer we get to the edge. technically, if we're really going from one regime into the other, they're probably going to be the same. So you get the same as what Jim Thompson looked at of the rollover effect and the signal to noise ratio issue, which basically gets the contribution of sea ice that doesn't get attenuated, that starts to play a more important role. So that sort of starts to decrease the observed attenuation, but it's probably not real. Yeah, that's what I think is going on.
Okay.
Does it make sense?
I think another possibility is I forgot which paper I read. I mentioned this to you once probably because the flow collision, like the very narrow room for the flow collision around MIZ around 0.9. So the attenuation rate will be maximum in that room and then decrease.
Yeah.
Maybe a
Yeah,
possible already. I don't know. Yeah.
Yeah, that could perfectly well be the case as well. I'm not entirely sure though in whether or not ice flow collisions how they scale exactly though. But it definitely could be a reason if that's yeah, if that's relevant
Okay,
here.
thank you. Any question from the audience? Okay, I think Joy, I think there are no question anymore. Thank you, Joy.
Thank you.
Alberto, so it's your turn. Thank you.
Yeah, I'm about to share, 1 sec. Can you see it full screen?
Yes.
Okay. So whenever you want, Chishan, can I go?
Yeah, yes, please, Alberto.
Okay. Thank you, Chishan. So good evening or good morning, depending on where you are around the world. I'm Alberto Meucci, and I'm a research fellow in ocean wave climate modeling, for those of you who don't know me, and also an adjunct scientist at the CSIRO, working for the Australian Climate Service on a major effort to try to understand the climate, the coastal wave climate around Australia at a national scale, high resolution. And so in this presentation, I'm gonna kind of give you an overview of what we've been working in the past year on evaluation and calibration of a global spectral wave model for a ETC generated wind wave climate, and ultimately supporting the extreme sea level modeling for the Australian Climate Service. That's because Australia, it's EU-posed in terms of location and very well exposed, to extratropical cyclones. And just to give you a little bit of a project overview, I'm working in the climate context. So extratropical cyclones play a key role as they are synoptic low pressure systems, which are very frequent, and they shape the Earth's weather patterns, and they have a global impact on the coastlines, generating large swells that propagate over vast distances. Ultimately, this is also extratropical cyclones are also significant drivers of global metocean extreme climate statistics. And in the Australian context, which is the one I'm focusing on, this is particularly interesting to analyze and do research on, because they may actually play a major role in for extreme sea level statistics, especially in conditions which we have in Australia and in some of the Pacific Islands, especially of fringing reefs, where the waves are playing a particular role, and the wave setup onto extreme levels, as you can see from this illustrative sketch that CSIRO did a few years back. So to analyze the waves and especially analyze the climate, we set up 2 or 3 years ago, this research model. It's based on an irregular grid, and it runs over a regular 0.5 degree rectangular grid in between -55 south and 55 north, and two curvilinear grids for the poles. It's forced with era 5 in this case. Actually, originally this model was actually set up for climate to run a climate ensemble, a CMIP6 driven climate ensemble, which I will talk about briefly later at the end of this talk. But in this case, we also use this one to evaluate some of these ETC conditions. And so we used ERA 5 as wind and daily with hourly wind forcing and daily CIs. We used a simple CI scheme from Tolman et al. 2003. And then we mainly focus on an ST6 parameterization for the physics with a DIA scheme for nonlinear interaction. And we also tested in a few of our studies also the impact of currents, and we saw that there wasn't major impact of currents on the global statistics. So we decided to go ahead and run our analysis with no currents. And the output, our 1 hourly output on a grid 0.5 regular grid with these spectral resolutions. So all of our work on the evaluation and calibration of this model stemmed from 2 studies mainly. One that I've done as a personal interest on the April 2021 storm that we have here in Victoria, which actually launched these big boulders onto the road. And it was quite a major, news shock. And so we decided to have a look at this storm. And as you can see, let me put the pointer. We kind of the image that you see is around that location, Cape Bridgewater that you see here. And then we backtrack the storm using a minimum mean sea level pressure storm tracking technique. We backtrack the storm into the Southern Ocean and Indian Ocean and try to understand how this one evolved, and it was modeled by our global wave climate model. We ran a number of tests on this, mainly to have a look at the minimum frequency resolution test to understand whether the big swell approaching the coast were affecting by the lower part of the frequency beams. And then we also look at 2 different wind stress calibration for ST6. These are very well-known calibrations that have been used. One was based on CFSR winds. The other one from Liu et al. In 2021 was for the hindcast, the ERA 5 hindcast, run very similar to this one with a drag coefficient factor of 1.08. And then we also had a look briefly at ST4, which I won't show here for a matter of time, and also at the impact of resolution, and compare ultimately with ERA 5 and ERA 5 hindcast waves, and some in situ and buoys and some remote sensing evaluation. Here, I'm just showing you one of probably the main outcome, or one of the main outcome of this paper was that backtracking the storm. Now we are looking at here a passing of the Sentinel-3B altimeter, and as you can see, the difference in the wave was quite major for ERA 5. And we all know that now, and there has been a lot of work done on correcting a little bit the winds, and John in first line on this, and then we kind of had a look back then of what was also the path for the waves and how it was performing along the track. And so what you see in here is a plot on the bottom right section where you have the HS in the y-axis, and then we just move along the track, stepping 1 hour each time. And then you can see that the base ST6 calibration, it was the lowest scoring one with very low value. And this dash line, this vertical dash line, is where these measurements of 17-meter wave height of the Sentinel-3B should be. And so we were they're practically out of these plot here. So even different drag coefficient, or even looking at ETA 5 hindcast or ETA 5 itself, we were still missing that energy, and we were kind of like, trying to understand this better at a global scale for then ultimately the wave hindcast for the Australian Climate Service and the calibration of it. On top of that, the second work that was the background for the overall evaluation of the wave hindcast for the Australian Climate Service and also the calibration of it was this Pacific swell propagation work that we've done with a student here at the University of Melbourne, where we tested a few calibration of the swell source term component, swell dissipation source term components in ST6. How did we do that? We took we started from Campbell Island, which is an island south of New Zealand, and we look at 19 different Great Circle paths, and we compare at every 1,000 kilometers, if maybe slightly more, I don't remember the spacing, but it was at around 1,000 kilometers each. We compared the energy, and so the HS observation from SAR observations and from our wave model. And what we found is that the major impact on reducing the bias, especially in this swell pool climate here, was a reduction of the negative wind input, which is a term which is part of the ST6. And so a reduction from 0.09 to 0.05 were actually improving a lot the statistics in this well pool region. We couldn't do much for this region because of the impact of the island. So what you see in here, this blue part in here, is because in these regions, all of these swell that were impacted by the islands, and as such, the model, especially this resolution, is still struggling a bit to get this the energy right. So then we moved on, and based on this, Stefan did also some work on the Auswave G3, which was linked to also these studies that we were working on. But he did a major work on trying to calibrate and understand a few different iterations of Auswave G3, and especially with focusing on ST6, which is the focus here in Australia. And then we took these settings of the Auswave G3, which is this time is a 3-layer SMC grid with a coarse layer of 0.25 degrees and then moving to 0.125 and ultimately to 1/16 of a degree close to the global coastline, which is this light green that you see in here. The grid was different, but the wave model settings were really comparable with what we did with our research model. And so we went on and we started having a look at this model and trying to understand how we can improve, especially for extreme waves and for the extratropical cyclone region, which is the one here that impacts the coast of Australia, and ultimately we believe will impact also extreme sea level statistics. And so the idea then was to have a look, and thanks to Stefan, who had a look at the ASCAT comparison over 10 years, and we wanted to have a look at and try to explode what happens at the extremes. And so what I thought about doing is actually, let's have a look at a semi-logarithmic scale, so then we can actually explode what is happening in the tail of the data. And as you can see here, the ASCAT is this dotted line in gray, and you can definitely see that the original ETA 5 winds were a bit underscoring from 20 meters per second and up. This is well known now. There has been also some of these calibration done already also in Europe, and so we worked a little bit on this, and based on the trials that were done already on Auswave G3, which is the forecast model here at the Bureau of Meteorology. We also implemented and we tested 4 different corrections to this wind. and which is barely a linear correction of the wind over a threshold. So the W core 1 would be our threshold, which in this case for the baseline was 23 meters per second, and then and a correction of 1.08, and then we moved on and we tried a few different ones. And so to test this, we looked at these 3 test runs, and we ran a number of satellite altimeter collocations. In particular, I looked at both buoy altimeter collocation and altimeter cross calibration, just to be sure that nothing weird was happening with the statistics at the extremes coming and the measurements coming from the satellite altimeter observation. And then we had a look at a few statistics, so the typical one, the bias, the Voermans correlation, and the RMSE and the scatter index. The advantage of in this case is that the very high resolution of 1/8 of a degree, well, very high, that's higher resolution than the previous model, 1/8 of a degree. We could practically pick almost at the resolution at of the satellite altimeter. So we were almost at the limit. So we had a look at 2 years. In this case, I'm showing you the 2011 collocations, which show the collocations from 4 satellites. We ran these tests. This is just the bias of the 4 different runs, which looked consistent also with the spatial distribution and the magnitude of the bias also in different years, such as, for example, the 2016. What you see in here is a little bit in the sea ice region, especially for Antarctica here, the satellite struggle in the observation, and we have a little bit of a high bias in there in the comparison, which is kind of expected, but we can also see kind of like the trace of the currents, that and a little bit of the bias of the current interaction, which is just a slight bias that we find in all of the runs. And ultimately, we decided to have a look at all of these in the same way as what I showed you before. So with a logarithmic, semi-logarithmic scale, but this time for the waves all over the globe. And so what happens here? I just then chucked out the 2 polar regions and just ran the collocations and then pulled all of these value together. And what you can see in here is that our original ST6 run here in the dot line. This is the city with the drag coefficient factor of 1, and with the eta 5 forcing was staying pretty low compared to the blue lines here, violet and blue line of the satellite altimeter. And so as we moved on and we kind of tested all of these corrections to the wind, we were pleased to see that we were moving this tail up, and actually that the wave model was working quite well. As you can see from this violet one, which is the one that ultimately we decided to go with, which is the ST6 W Core 3, so the third iteration of it. We managed to stay practically with the same bias all over the world, and even higher correlation and lower scatter index and lower RMSE, but we are actually pulling now the tail of the data, which is the one we are interested in, especially for the swell approaching to Australia, very close to what the observations are. And this behavior was actually consistent across domains. This was the domain that I kind of zoomed in for Australia, and that you see the same case, and that tells you that actually what is dominating these statistics is actually these extratropical cyclones, because this is the region where most of these data it's pulled from, these big waves in here. And as you can see again, our chosen calibration works now. It's working pretty well in comparison with the satellite. And again, this one just to show you that we further zoom in the area of Melbourne, we kept on having the same behavior. So we kind of said, okay, let's choose this calibration then for the wave hindcast, and that we run for 40 years for the Australian Climate Service. And then going back to the storm now, what happened is that, and what I was pleased to see is actually that just changing the wind and just tweaking on the wind, this is actually what we get now. And so we have much higher waves in the area, and we can actually pick almost the value of the Sentinel-3B. So not only on a global scale, but also in the single event that I was looking at, we are now doing a much better job. And here I have to apologize with Jan and Josh, because I didn't have time to put the ERA 6 prototype, which we had a look back then with Cape Bridgewater, and we were practically on the same path as our new wind correction. So the ERA 6 will sit here with the dashed line of our correction as well. But we needed, and it was important for us, to run it as well in our for our Australian Climate Service product. And so ultimately, on top of that, my research model, I've used that for wave climate studies and CMIP6 derived wave climate data. We've run an ensemble of it, an 8-model ensemble, and as we are providing with the wave hindcast the directional spectral boundary conditions for this domain in here that you see in here, which is our couple wave hydrodynamic model that we are running at CSIRO. Now I'm also providing the wave statistics for the future, and so for the projected CMIP6 derived statistics. And ultimately, what I did in here is actually having a look at the previous 7-model ensemble that was produced at CSIRO, that was used here in Australia and also around the world, which was an ST3 run with CMIP5 derived data. So it's a bit old. It was from 2016. We've updated it to SC6 run with an 8-model. And then we run our analysis, our pooling approach for extreme value analysis, and to find the 100-year return period. And through this analysis to a standardized variable that you see at the top here, we can actually bias correct this model and pool them together, and ultimately have a total of 189 years and 140 years for the CMIP5 and 240 years in total for the CMIP6 model, where we can evaluate our 100-year return period. And so I'm just showing you now the difference of now what we have in the extratropical cyclones region and what we had from the CMIP5. As you can see, the sea ice conditions are very different. Also because I'm picking from here the value coming from the wave model, and so in the wave model it's just we have not a number of values where we have the CI in some of the sea ice region, and this one is picked directly from the CMIP6. But as you can see, the winds are comparable. For the historical one, there is just a little bit higher winds in the ensemble taken from the CMIP6, but the waves were much higher in the previous model, the previous iteration, that from what it is now. And I believe this is probably due to the capping of the, maybe I'm guessing it's from the capping of the drag coefficient. And if we move to the future, we have a change in the wind field for both of them, but the major change is actually found mostly in the CMIP5 than in the CMIP6, and this, you can actually see these with the changes in the winds that we can see from this almost 200-year data for CMIP5 and then the CMIP6 in here. And so we believe that both the wind that was here higher and the wave model are actually playing a role in this major change in here, which is ultimately this signal is not very well felt anymore in the CMIP6 driven data. And so this is something of interest that I'm still kind of investigating, but definitely the ETC region, it's of high interest, and still some areas with increase of wave height approaching Australia, which will play a role also for our coastal coupled wave hydrodynamic model, and that we will analyze further. But in general, just to take you to the conclusion, there's still a question on the extreme calibration, I guess, against altimeters. There is a range of uncertainty surrounding these significant wave height values. We've seen some work on this recently, and the measurements from the altimeter in storm condition, and we are also trying to discern the reason behind the new climate patterns, both for wind speed data set and that are due to both wind speed data set changes, but also especially improvements in the wave model physics, which played a crucial role. And then ultimately, we are also, for the regional part, I'm also doing analysis, and we just published a paper on climate dynamics on wind downscaling using some regional climate model that we run here in Australia. And then through that, finally, we like to, with a coupled wave hydrodynamic model, we'll estimate what is the wave setup contribution of the ETC generated waves, especially for these regions, exposed to Southern Ocean and the Indian Ocean ETC generated wave climate. There it is. Sorry if I've been a bit long, but yeah, that's the end of my talk.
Okay, thank you, Alberto. Don't worry, we have plenty of time. So, any questions? Oh, Tom.
Alberto, thank you for your talk. Very nice. Could you comment on this first question on your sheet here? What issues are there regarding extreme using altimeter data to calibrate extremes? What are the main challenges there?
For the calibration, you mean?
Yes.
So there has been a recent paper about the actually measurements of significant wave height from altimeter in storm conditions. And it has been shown, this is a paper by Marine De Carlo and Fabrice, which it has been shown that there is a little bit of a range of uncertainty over the significant wave height measurements. And so we've actually calibrated everything based on what we have, which is a straight value from the Australian Ocean Data Network. And what is usually done with this collocation. But yeah, there could be also a little bit of a range of, in some cases, higher or lower values for the altimeters, which we really don't consider in here.
Okay, thank you.
Any question?
Can I comment? A clarification so that people will know what's coming. So what Alberto presented as ERA 6 prototype is actually based on the latest model from ECMWF that became operational last week. So it's our 49R1 system. So on which ERA 6 will be based, plus a few other changes. But one feature ERA 6 will have, which is for the first time in ECMWF reanalysis, the reanalysis system will also see surface currents. So the wind that will be generated would have seen the surface currents. This is the first time a reanalysis product. So it gives us an idea of what the wind will be, this data that Alberto is showing. But the true nature's ERA 6 is yet to be shown, and it's supposed to be even better.
Yeah, and again, I'm sorry, I actually messed up with the years, so I asked you for the wrong year. It was 2021. That's why I couldn't run the comparison. But maybe we can talk further on that.
Sorry, John. For this point, is ERA6 winds stronger than ERA5 winds?
Yes, they're stronger in the high regime, even though some people in the wind energy thinks they are still a bit too low. But you still have to realize this is a global reanalysis at still the finest resolution will be 14 kilometers in ERA 6, so it still has some limitation. But yeah, we've worked really hard to try to improve the high wind part of it, because we know, as Alberto has shown, ERA 5 has a strong underestimation. We think we have partly solved this, but it's not 100% perfect, I would say. It still has a bit of underestimation, but it's a lot less than ERA 5.
So what's the key part for the underestimation of extreme winds in ERA 5?
Is the coarseness of the global grid and too strong wind wave interaction. So I've worked really hard in the coupling between wave and atmosphere, and ERA 5, this coupling for strong wind was too strong. If you express this in terms of a drag coefficient, the drag coefficient that the ST3 physics return was way too high. And so over the years, we've moved to ST6 plus now this work I've done with Peter Janssen, which is part of this latest model, which essentially, if you plot it in terms of a drag coefficient, you see you reduce sharply the drag coefficient for high wind. And as in a coupled system, that means how you on average get slightly higher strong winds.
Okay, thank you. Any question from the audience?
Hi,
Gudila?
Alberto, thanks for your talk. Could you go to slide 15? I think it was 15 with your comparison with the new ST6 simulation.
Is it this one? Can you see it?
Oh, yes, that one. Now, it's just about the HGS on the right slide. It's in your new simulation, this HGS on the right one is still high after the 0 UTC. Do you have some explanation for this?
That's just how the wind pattern is. So the extratropical cyclones actually swing through and went from and stopped in this area that you see here, where I'm pointing with the laser. That was the highest part of it. It stopped for a while. It was blowing, and then it started again blowing harder. And that's just, the response of the wave model to two different, stages of the extratropical cyclone. So these movements are not regular. As far as I could see from here, they kind of slow down and then they pick up again. And that was the case.
Oh, okay, thanks. I got it.
Okay. Alberto, have you tried to use the CFSR winds for this case? Because the CFSR wind is high for high wind speed.
No, I haven't. But that's because mainly the Bureau was focusing on ERA 5, because main reason for it is that they are downscaling as well ERA 5 on the regional climate model, and so we needed that consistency. So I didn't end up testing CFSR, no.
Okay, so for this figure, for this slide, when you backtrack when you backtrack the wave event, can you, find the source of the storm? Is it does it agree well with the weather chart? If this is a central tropic cyclone, or
so the only thing we could do is to actually see if we have any matches with the altimeter. So here maybe it's not that clear, but if you see in here on the left side is the Sentinel-3B, and you see it's Friday, April 9 at 1 a.m. UTC, and so it corresponds to the area in here, which I put this vertical dash line. And as you can see, that the measurements kind of were fluctuating in between 16 to 17 meters for the waves. and the wind was up to 30, 31 meters per second. And so the value, it's around this in the area where we are, you know, where there is this dashed line. So this is just to show you that this 17 is actually should be here.
Okay, thank you.
Yeah.
Okay, it's 5 o'clock. I guess that's all for today's seminar. Thank you for the 2 speakers and thanks for the audience.
Thank you.
Let's see you next month.